Welcome to Durham University, and this is my pleasure to talk to you today very quickly because James is going to take the stage today. So my name is Mathilde Josac. I'm a professor here in the Center for Extragalactic Astrophysics, and so I'm an astrophysicist. And I look at galaxy clusters, so very massive objects in the universe, plenty of Milky Ways, if you want, in the same space. And I'm trying to understand what dark matter is made of using those. But that being said, I'm here to introduce James. So James Osborn, he's also a professor in astronomy. He works at the Center for Advanced Instrumentation, and he's the new founding director of the Space Research Center in Durham. And so James is working on instrumentation. So that means initially he was working on instruments actually for us astronomers, so we could better see the night sky from the ground. So he's been working on developing instruments and trying to understand how the light goes through the atmosphere before reaching our telescopes. And following that, this is not just for astronomers to look at the sky and have and try to understand the information that comes from space. That can extend to actually satellite communication. And so James then moved on from, well, still in astronomy, but kept on opening his research interest and got into space sustainability. And this is basically what he's going to talk about today. So I leave the stage to James, and I hope you'll enjoy the lecture.
Thank you. Thank you, everybody. Thanks for coming. So my name's James Osborn. I'm a professor of space science, as Mathilde says, in Durham University. I'm also the director of our new Space Research Centre. This is something that we launched just a few weeks ago, actually, so you may not have heard all about it yet, and that's fine. I'm not offended if you haven't heard yet, but you will hopefully hear a lot more about it in the coming years, because actually community engagement is one of the big things we're very keen on. And the reason that we're starting this space centre now is because the whole space sector is changing. Okay? And whereas most space centres traditionally are all about technology and engineering and developing the emerging capabilities for the space sector, we're a little bit different. We're a very interdisciplinary space centre. So yes, we're focusing on technology and engineering, but we've also got people who are thinking about space law and governance and international relations, because we're now at a time where that's becoming important. So today I'm going to tell you a little bit about the history of space exploration, where we've got to today, and then think about why this space sustainability and interdisciplinary space sector is required today. Okay, so we'll start. Clicker works. There we go. Okay, here's a figure for the number of objects launched into space as a function of years, from the 1960s right up to 2010. Okay, so if we look right at the beginning, the first satellites launched to the space at the end of the 1950s, 1960s, we have the space race, get to the moon. And what we see is we're launching around about 100 satellites into space for 40 to 50 years. They're all blue, so they're defense satellites. Okay, these things are the size of a bus. They cost hundreds of millions of dollars. They're really complex. These are the kind of things where failure is not an option. They have to work. Okay, but then something happens around 1990s. We start to spend less on defense in space. That's the end of the Cold War. Okay, so we've realized that actually we don't need to have so much defense in space, and that sort of defense part, the blue curve tails down. And then we see a sudden blip in the yellow, and that's interesting. This is commercial sector acting in space. So these are people who have realized that, okay, there's an opportunity here. We can use space for the quality of life of everyday people, not just for defense. And there's a lot going on, right? It shoots up really quickly to about 200 objects per year. But then there's a hard cutoff as well. And what happened there was the Challenger disaster. Okay, so from the 1980s right through to the 2000s, pretty much everything in the US was launched on the space shuttle. Okay, the space shuttle was incredible. It was the workhorse of space launch. And it was this incredible thing where it would launch vertically, but then come down like an aeroplane. So it's really good for getting stuff up there. But in 2000, there was a disaster. One of them exploded on launch, and that was the end of that program. Okay, so suddenly this commercial activity hits a hard stop because of the lack of appropriate launch vehicles. Right? And then there's not much really going on, 100 or so objects per year. But if we zoom out to now, let's look what happens. Okay. We see this sudden change, this explosion of activity. Right? And whereas this stuff was all the size of a bus, hundreds of millions of dollars, failure is not an option, what we're seeing here is 2,500, 3,000, 4,000 objects launched per year. Right? That's incredible. But these things aren't the size of a bus, they're this size. Okay? So now we're at the stage where we're launching small satellites, and because of the progress in technology, this is still super useful. Right? So these are called CubeSats. There's a lot of CubeSats out there. They're built in what we call units, right? So this is a unit, 10 centimeters by 10 centimeters. So if you want to build a satellite, you could fit something in here. If that's not big enough, you can join them together to make 3U, okay? This is a 3U satellite. It's something we've been working on Durham University to be launched in the next couple of years. And these things are designed to go in the rockets, in the smaller launch rockets as well. So this is a rocket designed by our undergraduate Spaceflight Society, where they recently launched 18 kilometers over in the US, which is the highest UK amateur launch record, which is quite incredible. It's all done by undergraduate students. So what's happened then to enable this sudden growth in activity in the space sector? Around about 5 years ago, this all kicked off. And what happened was this, okay? Reusable rockets. The idea that you can launch something into space, bring your rocket down again, service it, do a few tests, and then relaunch. It's incredible. And that brings down the cost of launch and opens up the space for anyone who wants to try something. So whereas for the space shuttle, you were talking about $50,000 to launch 1 kilogram into space. That's quite expensive, right? That's why these things have to work first time. Now, with SpaceX, it's $1,000 to launch a kilogram, okay? Within this room, we could probably club together, put a camera or something in here, and launch it into space and see what happens. We can afford to do that, and so can commercial companies, which is why people are trying things. Whereas back in the day, you would have to rigorously test even a resistor that you want to send into space. Now you could put a Raspberry Pi in a satellite and see if it works. And that's a huge paradigm shift. And that's why we've seen that sudden increase. And that's why now is a very exciting time to start getting into the space sector. Right. Space applications. So now we're going to think about what do we do in space? Why is this important? Why does it support our quality of life? So here's a question for you. What do we currently use in space? Why do we use space? Any ideas? You can shout them out.
Starlink internet.
Communications. Right, communications is a good one, there's one. There's 4 big ones, okay? Any more ideas?
Spying.
So say that again?
Spying.
Spying, yeah, so that could be Earth observation. It's taking images of the Earth. Exactly, good one. Okay, 2 more?
Research.
Research science, yes, absolutely. And there's one more. You've all got it in your phone. I use it to get here even though I know where I'm going.
GPS.
GPS, exactly, satellite navigation. Right, those are the big 4 space applications at the moment. Let's look at them in a bit more detail. This is the James Webb Space Telescope. Who's heard of the James Webb Space Telescope? Yeah, pretty much everyone. Okay, this is an incredible piece of engineering. This thing cost about $10 billion, about 20 years to develop. The whole thing is the size of a tennis court, so it probably wouldn't fit in this room even. Here's a model of one of those mirror segments so you can get an idea of how big the whole thing is. In Durham, we've been involved with the scientific process of getting this thing going, and it's used. Martin Ward, sitting in the corner over here, has been very involved with that. You can talk to him later. We've also built components for some of the instrumentation on James Webb Space Telescope right here in Durham, so we have a strong influence. And the whole point of this thing is to try and unlock the secrets of the universe, to discover what is dark matter, dark energy, to try and find planets orbiting distant stars, and beyond that, see if we can find the fingerprints of life. Can we find the evidence for extraterrestrial life in the universe? What is our place in the universe? But why do we put this in space? Right, this thing is miles away. It's the other side of the moon. It's really far. So, but why? Why don't we have James Webb Space Telescope in Durham? Any ideas? Shout it out.
Avoid interference from this atmosphere.
Atmosphere, exactly that. exactly that. Okay, if this thing was in Durham, right, one, it's always cloudy, so you never see anything, okay? Two, the Earth's atmosphere blocks out some of the wavelengths that we want to try and look at. For example, the atmosphere blocks out X-rays. X-rays are super useful if you want to try and study black holes, for example. Luckily for us, the atmosphere stops it getting to the surface. If it didn't, we wouldn't be here, okay? The other thing that the Earth's atmosphere does is it has turbulence, okay? You know when you look at if you look at the stars and they appear to twinkle, you've all seen that, there's a nursery rhyme about it. That's due to the Earth's atmosphere. That's not inherent twinkling in the star. And what's happening there is that air of different temperature has a different density and therefore a different refractive index. And a diffractive index changes optical path length, right? A bit like a lens. So essentially the atmosphere is acting like a lens and distorting all of the rays. Here's an animation. So if you look at a star through your eye, okay, you don't really see this, you just see it twinkling a bit. But if you look for an 8-meter telescope, this is what you would see. And it's broken up into speckles, it's changing color as well. Sometimes if you look at stars and the turbulence is particularly bad, they appear to change in color as well, you may have seen that. And that's a chromatic effect from the Earth's atmosphere. But because our eyes are quite small, we're not really that sensitive to it. You know, sometimes when you look down a hot road and you see it sort of shimmering, that's the same effect. So we've built this device here, which actually can visualize turbulence in a much easier way than your eye can, because we're using a big mirror. And if I put my hand in here, you can see the heat rising off it, right? And that's because we're using this big aperture, so it's much more sensitive. So the light is really sensitive just to that small amount of heat. My hand's not that hot, actually. And you can see all of that change in refractive index. And that's why we don't have so many telescopes on the ground, but we rely, well actually we do have most telescopes on the ground, but we rely on the space segment as well for that extra precision that you can't get on the ground. Okay, quick question. How many space telescopes do we think are in orbit right now? Shout it out. Doesn't matter if you're wrong.
500.
500, good guess. Any advance on 500? 1,000? It's a little bit less than that. It's about 100, okay? About 100, not all operational. But there's about 100 satellites, science satellites in orbit at the moment. The next one, position, navigation, and timing. Someone said GPS. GPS is a system of satellite navigation. Okay? Satellite navigation works by, essentially, you have a number of satellites out there in orbit, and they're just constantly shouting the time, right? Just going, it's 10:58, it's 10:58, it's 10:58. And if you're telling me it's 10:58, and I receive that at 10:58 and 3 milliseconds, well, we know the speed of light is about 300 kilometers per millisecond, so you're about 900 kilometers away. Right? That's no good because I could be anywhere in a sphere centered on you, so I need another satellite to also be shouting out the time, and then I know how far you are to the other one. Okay? And if I do that 3 times, then I can triangulate my position. But actually that's still not quite good enough, because one thing we're assuming there is that I know the time, and I don't, because my watch and my phone isn't good enough. So I actually need 4. That's why we need 4 GPS satellites in order to trilaterate really, your location. But it turns out that satellite navigation is super useful for lots of things, you know where you're going. But one of the biggest applications of these satellites, which are constantly shouting the time, is that time signal in itself. This is the first time that we were able to globally agree what time it is. Right? Before this, I thought it was 10:58, you thought it was 10:58 in 3 milliseconds. We couldn't agree on that. And that's really important for things like financial transactions. If I buy something with my card on my phone, boop, then that is precisely time-stamped. And it needs to be for financial markets to work properly. Otherwise, you end up with people selling things before they're buying it, and everything gets in a little bit of a muddle. Okay, how many position, navigation, and timing satellites do we think are in orbit at the moment? Shout it out. Shout. Some 5,000, 1,000.
32?
32?
I think.
There's a few hundred. There's a few hundred position, navigation, and timing satellites at the moment. Right, Earth observation. Someone else mentioned this. Earth observation is really critical for climate change mitigation. The vast majority of the data we feed in to climate models comes from space. Okay, and that's because we get that bird's eye view, we can see what's going on. Really, any sort of climate change mitigation relies heavily on modeling the Earth's environment and the Earth's climate. To do that, you need the input data. That input data comes from space. It's also useful for weather forecasting, for example, where we get that bird's eye view and we can see the weather systems. That's tied to the climate monitoring. And then the other applications are things like agriculture and land use. So it may be that a farmer can pinpoint exactly where in their farm they need fertilizer or pesticides, for example, rather than just spraying the whole farm. And that's very valuable resource. It's an expensive thing to do, and it's also bad for the environment, so it's win-win. Disaster response, things like trying to guide response teams, emergency teams on the ground in certain disaster zones. It's also used as surveillance, obviously, as well. How many Earth observation satellites do we think are in orbit at the moment?
8.
Sorry? 750, good guess. It's about double that, about 1,500, actually. Just get an idea of numbers. Here's an example of Earth observation. So the one before we showed the climate, the global scale. This image is from Satellite View, which is a company based in the UK, actually, that uses infrared cameras to look very high resolution at the ground. So infrared is effectively measuring temperature. So this is a map of temperature in the center of Rome, right, where red is hot and blue and black is cold. And now what we can see using Earth observation is that we can pinpoint individual buildings which are radiating. And this enables us to direct that insulation that might be needed to make in order to reduce that radiation, right? Which reduces energy use and is therefore good for the environment as well. We can do it house by house now. You can identify where that insulation needs to go. Communications is the next one. This is an interesting one because the vast majority of our communications doesn't go anywhere near space. Right? If I was to phone you, that data wouldn't go through space. It'd go to a local phone mast. It might go through some optical fibers. If I was to phone someone in Australia, it wouldn't go to space, right? It'd go through optical fibers. But there are some people in the world that don't have access to high capacity, high bandwidth fiber optics. There are places in Weardale and Teesdale, right? Places in County Durham that don't have access to high bandwidth and high capacity fiber optic internet. And this is important because it brings us essential services like healthcare, education, finance, entertainment as well, irrespective of population density. So now you can have a satellite dish on the side of your house and you have access to those essential services. It brings communications to ships and planes, obviously. They don't have any fiber optics connection. And it's super useful for resilient backup as well. If you've got a network that is so important that you can't afford for it to go down, for example, like a financial network or a military network, then you'll probably use some sort of space backup for resilience. Okay, there are two ways of doing this. The first one is by using what's called geosynchronous orbits. Geosynchronous is a very special orbit because the rotational period is about the same as the rotational period of the Earth, which means that if you put a satellite dish on the side of your house, it's always going to be pointing at the same satellite. Right? So it's really easy. They're also really far away. And because they're really far away, put a torch on, it means that they can cover a large area of the globe. Okay, so with one satellite, I can service a whole continent. With 3 or 4 satellites, you can service the whole world. Now these things are, these things are very big and very expensive, and they're very far away. They're difficult to maintain. The problem with them is that because they're so far away, they're about 36,000 kilometers away, so they're 3 times the diameter of the Earth away. Because they're so far away, the light travel time from the Earth to the satellite and back again is a significant fraction of a second. So if you're trying to have a voice conversation, it's noticeable, it's awkward, it doesn't feel right. So it's great if you want to stream a video, but it's perhaps not very good for communications. The alternative is to use low Earth orbit. Okay, so now we're in the area where we can launch lots of small satellites. If we have satellites close to the Earth, then they illuminate a much smaller area, so you need lots of them. So we're now thinking of having constellations of hundreds to tens of thousands of satellites all around the Earth to provide that low latency, short path, okay, connection to space. Now, because they only illuminate a small area, they also have to be interconnected. So we end up with this mesh network in space. And it all gets rather confusing because there's a lot going on. It's very dynamic. This is a huge, huge application. Actually, most of the satellites that are launched at the moment are all going to low Earth orbit for communications. How many communication satellites do we think are in orbit at the moment? Any guesses? Sorry?
Tens of thousands.
Tens of thousands is a good guess. Any others?
Too many.
Sorry?
Too many.
Too many. That's an interesting answer. Okay. There's about 8,000. So yeah, again, the plan is hundreds of thousands, right? By 2030, there'll probably be hundreds of thousands of these things. In terms of numbers then, let's think about the economy, the space sector. So the global space economy is generally valued about $500 billion, okay? And that's projected to rise to 2 trillion by 2035. These are really big numbers. In the UK alone, then the UK space delivers about £20 billion to the UK economy, 50,000 jobs. That's probably the most important bit. It's a huge number of jobs. If you include everything which uses space as a service, so for example, if I have a business that uses GPS to make sure I deliver packages to the right place, and that's include that in the value as well, then it's more like £370 billion per year to the UK economy. That's £1 billion a day, right? That sounds like a big number, but actually, I've no idea. I'm not an economist. I don't really know what that means. So instead, I'm a physicist. Let's do a thought experiment. Let's play a game. The day the satellite stood still. Imagine you wake up one day and there's no connection to space. We've lost connection to satellites. Don't worry why for now. We'll come to that later. But let's see what happens. The first thing that happens, we lose connection to those remote locations, right? Those early adopters up in Weardale don't have their high bandwidth capacity anymore. Okay, so that's the thing. Planes are grounded, ships are returned to port because they don't have the satellite navigation to support them. There's chaos on the roads because there's no fleet management. If you're emergency services or a haulage company, you need to know where you're going and where all your vehicles are so you can manage the flow of those vehicles appropriately. You can't do that anymore. And some of you, well, I remember back in the day when I didn't have GPS, the GPS was made available about 1990s, I used to write down directions and then sellotape them to the dashboard. People were doing that again. It's chaos, right? The roads would be a mess. What happens next? Weather forecasts become even worse. Right? We know they're quite bad anyways. It's probably not a big deal for us. But there are some industry that rely on the weather forecast, for example, agriculture or fishing. This becomes an issue. There's no phone signal. That's an interesting one, isn't it? Because I told you before that none of our data really goes through space. So why have we lost connection to mobile phones? Well, it turns out that in order for these networks to work at high capacity, and that's what they are, all of the networks, whether it's mobile phone or internet, is working really close to capacity. To have a network which is routing information, the flow of data through this network is really difficult, and it relies on very precise timing. So the mobile phone towers, they need to have very precise timing to know the order of the data coming in and going out and control that flow. Without the GPS signal with the timing, then our networks, internet and the mobile phone networks, will crunch to a halt. There's a problem in industry as well, because there's no shipping, right? All of those ships carrying oil have returned to port. So the cost of fuel goes through the roof, right? There's a demand, there's a lack of resource, which is a problem. So our industrial machine grinds down. What else happens? Financial markets collapse, okay? I've already told you that to pay for something on my card, I need a timestamp. We don't have a timestamp anymore, so all our digital financial transactions are rejected. On top of that, the stock markets are hit because they're trying to trade at millisecond level, and they don't have that agreed timing between London and New York. So people are buying or selling before they're buying, and everything gets in a mess and it all comes down. Power grids all fail, right? The power grid relies on really precise timing to control that flow of energy, the supply and the demand, the energy generation. You generate too much energy, you don't have anywhere to go, then it's going to damage sensitive equipment, which takes a long time to repair. There's chaos in our shops because we're relying on local produce from the local farms. We don't have that haulage anymore, bringing in food from around the world. So we've got a lack of food on the shelves. To some extent, that doesn't matter because you've got no money to pay for it anyway. So we're in this situation where you've got no money, no power, no communications, no food, just because the satellites have stopped working. I don't think most people really understand how much space supports our everyday quality of work. And this is what we're trying to get across. I don't know, if I'm honest with you, how realistic that story is. Okay? All of those things are true. All of those systems rely on space data. There's some redundancy. Maybe you can bring out some different ways of mitigating some of it. But what's the key message is that we rely on that data every day. I've used AI image generation a lot in this talk, as you'll have noticed. When I put in that scenario, no power, no money, blah, blah, it refused to generate it. So we've had to have chaos in purple. Right? This is the image to represent that situation. Okay, so what would cause such an event? There are three big causes, really. The first one is a coronal mass ejection. This is a wave of charged particles that are released from the sun and come hurtling towards the Earth. The charged particles corrupt the memory in our satellites, and the magnetic fields induce currents in delicate electronics. So our satellites are controllers, they're out of control. Right? They're up there in orbit, they'll stay in orbit for hundreds of thousands of years, but we can't control them, we can't do anything. The next one, cyber or conventional warfare. The idea that someone could hack into a satellite. This has been demonstrated. People have hacked into satellites, luckily their own satellites for now, that we know of. Physical warfare, the idea that we could launch a missile from the ground to destroy a satellite, right? Or even from space and destroy a satellite. This has been demonstrated. People are destroying their own satellites as a show of strength, a show of capability. This is already happening. The last one, space debris. If two satellites were to collide in orbit, they would make a lot of debris. Right? When two cars crash, there's a lot of stuff comes off. That stuff stays in orbit. It stays in orbit for hundreds to thousands of years. If some of that debris hits another satellite, then it creates more debris, right? Which will go on to hit another satellite, creates more debris, and so on and so on. So we have this cascade. And before you know it, you end up in a situation where we lose access to that valuable space orbit. Right? And you can imagine that those first two could easily lead to the last as well. So let's look in a little bit more detail now about the space environment. Here is an image which shows all of the active satellites in orbit at the moment. The Earth is somewhere in the middle. Okay, you can't see it because of all those green dots. Those green dots are satellites. And the ones in the middle are low Earth orbit. Okay, there's loads of them, obviously. Some in the around in sort of the middle bit of the image. They're all your GPS satellites, satellite navigation. Then that ring around the edge is the geostationary, so the big communication satellites generally, and the weather monitoring satellites. If you add up the numbers that we spoke about before, you get to about 10 and a half. This is a bit out of date now, probably over 11. So there's about 10,500 active satellites in orbit at the moment. Well, that's not everything that's up there. Until recently, well, still now even, if we launch a satellite in space, we tend to leave the rocket up there as well. The rocket bodies, there's about 3,000 of them, 2,000 of them in orbit. They're particularly bad because they are enormous and full of jet fuel. So if anything hits them, then that's a huge amount of debris that we're putting exactly where we don't want it. Inactive satellites, Until recently, if a satellite came to the end of its life, it ran out of fuel, it wasn't useful anymore, we would just leave it there. Okay? There's about 3,000 of them. These are particularly bad because they're out of control. We've got no way of moving things around if we think there's going to be a collision. Interesting, okay? 10,000 uncategorized objects. These are things that we know are there because we can see them. Even in Durham, we have technology to monitor and track satellites. And most of the things we see are these uncategorized satellites. We know they're there. We know where they are. We don't know what they're doing. We don't know who they belong to. They're just there. Right, then we get to debris. So at the moment, there's about 10,000 pieces of debris in orbit. These are things that we know are there, that are trackable. So they tend to be fairly big because we track these things with radar, right? So this is very much a minimum. At a minimum, there's about 10,000 pieces of debris up, which brings you to a grand total of about 40,000 objects which are regularly tracked in orbit. At any one moment, there's about 3,000 active conjunction warnings. Conjunction warning means that we think these two things might collide. When we get those warnings, actually, we don't do anything about it, right? Because the data isn't good enough. The data is incomplete and imprecise. And you can imagine 40,000 objects. There's probably about 40,000 cars in Durham, right? Welcome. There's probably about 40,000 cars in Durham. Imagine those cars scattered around the surface of the Earth. The probability of them seeing each other is actually fairly low. So here we're relying on the fact that satellite is small and space is big, so it's probably okay. Now imagine that those cars are traveling at 8 kilometers a second, right, which is your orbital velocity. At 8 kilometers a second, you can get from Durham down to London in less than a minute. Right? You go right around the whole world in 90 minutes. And that changes the balance in your head a bit, doesn't it? Because now you're thinking 40,000 objects that go around the world in 90 minutes. The chance of a collision, well, it's non-negligible. Right? It's possible. Here's a little animation of all of the satellites above Durham tonight. Okay? And I think there's probably more here than most people realize. See that belt, the stationary satellites? That's the geostationary belt that we spoke about before. That's down the south because it's around the equator, so we have to look down onto it. All those other ones are all the satellites in low Earth orbit that we spoke about before, mostly communication satellites. Over half of the satellites in space are Starlink communication satellites. But it's a very dynamic environment. Nobody really knows where everything is or where it is going. And that gets us to this, okay? So this is a nice demonstration of, I think, what's going on. I've got another plot here where we've got, again, a year along the bottom from the 1960s, the very beginning of space exploration, right up to now, in 2024, against the number of objects in space this time. So this is the total number of objects in space. You've got that unknown stuff that popped up recently, that's the uncategorized objects that we saw. But I want you to look at the light blue, which is the satellite debris. And what you see, okay, there have been some accidents and there's a small amount of debris trickling along until about 2010. Something happens in 2010, right? In 2010, the Chinese destroyed their own satellite as a demonstration. So, yes, we can do this. And that tripled the amount of debris in orbit. That number never goes down again, right? Because it's in orbit, it's orbiting for hundreds to thousands of years. And what you see, if you look at the trace on the right, this is a trace of all the tracked debris, the big bits, not the small bits that we can see in orbit. And it's not a nice constrained orbit, right? It covers a lot of altitude range. It's covering a lot of orbital shells. So this is a big problem. This means that anything, all of those communication satellites we're talking about, need to go through this debris shield, this debris shell at some point. So one event has tripled the amount of debris, and it only goes upwards. So although the probability of a collision is low, and getting higher as we launch more things up there, actually the impact of that is really high. Okay? It's really, really strong. So there's a demand. We need to know where everything is all of the time. We don't yet. Which feeds us on, right, to space activity management. With aeroplanes, we have air traffic control. Right? Air traffic control tells aeroplanes where they can go, how they interact, who flies to the left, who flies to the right, what order they land in, all this kind of stuff. That can't work in space, can it? Because the satellites go around the whole world in 90 minutes, so trying to hand over between jurisdictions is challenging. But really, the principle is the same. We're not really talking, no one's really talking about space control. What we're talking about is management or coordination. What we need, first of all, is a technology to monitor, to understand where everything is and where it's going. Then we need governance. We don't really have strong, hard governance for space management at the moment. This is the rules of the road, the highway code. Right? It's not there yet. And then we need coordination. And coordination in this sense means that operators from the US can talk to operators in Russia or China potentially and organize how we're going to avoid these collisions. That doesn't really happen yet. And this is really the focus of our new Space Research Centre. It's all about that holistic view of bringing together the people who are thinking about governance with the people who are thinking about international relations and technology. And the point is, there's probably people in the room here who want to be in the space sector, but perhaps aren't that interested in science, technology, engineering, and maths. And that's okay, because actually, space law, governance, international relations, marketing, politics, all of that is super critical for the future of the space sector as well. There's a lot of words on here, but don't worry about it too much. This is my map of space sustainability. This is what we need to do to make sure that we have a sustainable future in space. You start in the top left, space situational awareness. Right, this is the facts. We need to agree on the facts of the environment. What is happening up there? Where is everything going? And then we have on the top right, this is more the military side, okay, space domain awareness. For the facts, we don't really care what it's doing or why. Right? For space domain awareness, we do. Then we care about the intent. What is it doing? Why is it doing it? And that brings in that trustworthiness. Do we trust this object is doing what it says it does? It's an interesting question. And once you've got both those things, then we can think about global space traffic coordination or management, which brings in that regulation, the highway code with the coordination. And only when we've got all of that can we start thinking about a sustainable future in space, making sure that resource, that environment is there for future generations. And that's when we think about business models, sustainable business models, life cycle assessment, right through the supply chain of the satellites, through to planning of demise. At the moment, at the end of the life of a satellite, what we do is we generally bring it down into the Earth's atmosphere and burn it. It's been a long time since we thought burning something in the Earth's atmosphere was a good way of disposing of our waste. That really needs addressing. Circular economy in space is all about servicing, manufacturing, debris removal, taking those defunct satellites, sending some robotic tug up there, grab it and bring it down. We could do that. International relations, geopolitics, obviously, needs to be addressed. Right. Now we're going to play a game, okay? Waste of space or out of this world. I'm going to give you some ideas of what people are thinking about for the future of space. And I need you to put your hands up whether you think it's a good idea, out of this world, or a bad idea, waste of space. Okay, this is about thinking about the future of the space sector now. All right, ready? The first one, asteroid mining, right? What we're going to do, we're going to launch some rockets. We're going to go out, find an asteroid that's coming somewhere near Earth, grab onto it, pull it back to geostationary orbit, maybe the moon, depending on what you want to do, send up lots of robotic spiders, drill the thing, try and find those precious metals, lots of gold, lots of platinum, bring it back to the Earth, flood the market, sell it, make everyone rich. What do we think? Hands up for out of this world. Good idea. A few. Hands up for waste of space. Okay, you kind of split there. I think that probably reflects the community as well. Some people think it's a brilliant idea because it's access to lots of materials that we're currently are rare on the Earth. But it comes with a risk, right? You're bringing an asteroid into a close Earth orbit. That's not without risk. The other question is whether it's actually economically feasible, because we don't really know what the composition of these asteroids are. You could get there and it's just a load of rock, right? You don't know that it's going to be made of gold. Imagine trying to send a rocket up and changing the orbit of an asteroid. That's going to use a lot of fuel as well. That all needs to be got up to orbit somehow. Right, next one. In orbit, servicing, assembly, and manufacturing. What we're doing now is we've got factories in orbit that are going to extend the lifespan of satellites by refueling them, right? We're going to go out there, we're going to grab a satellite, we're going to inject it with more fuel to extend its life for another 10 years. Or maybe we'll grab it and put on an extra camera or a telescope or something to give it a capability that it didn't have originally. Maybe we want to do some manufacturing in low gravity, okay? There are people who want to, for example, 3D print lungs or a heart. You can't do that on the ground because it just collapses into some horrible sludge. You can do that in orbit where there's no gravity. You can print a lung and bring that down where it could be used to save someone's life. You could recycle old satellites, right? You could take a communications array off that one, you could take a solar panel off that one, put them together and build a new satellite in orbit rather than launching everything new every time. What do we think? Good idea? Hands up for a good idea? Yeah? Anyone think it's a bad idea? One. Brave. Good, I like that. Generally, I think it probably is a good idea. It does have risk, right? There definitely is risk. The risk is that to make that work, you have to get the satellite to come into a close approach with another satellite. And when that happens, there's a chance that there may be collisions, which creates more debris. But generally, I think it's pretty accepted that this is going to happen relatively quickly as well. Right, space maneuvers. Okay, what we're going to do now is get a satellite up there, which we'll call a tug, and that can then grab onto other satellites and move them around. Right, so one thing you may want to do is to grab an Earth observation satellite. So when you want to look at a particular area, you can get your Earth observation satellite with a nice big collecting, and you can point it down that thing and get it nice close to the Earth so you get good high resolution. And then when you've finished with it, you take it back up into a higher orbit where it's nice and safe. Maybe you do that. Maybe what you do is you grab onto it and then you find an old satellite and you take it out of orbit and burn it in the Earth's atmosphere. Or better than that, you take it somewhere else, right? And you deal with it either in your reprocessing plant or in a graveyard orbit somewhere. Okay, who thinks that's a good idea? Some of you, yeah? Who thinks it's a bad idea? A couple of you, yeah. I think, again, like the last one, it's generally thought to be a good thing to do. By using a tug, for example, to do the deorbiting, it means that you can extend the active life of the satellite in the first place. So rather than spending the last 6 months of a satellite deorbiting itself, you could use that for the full 6 months and then get something else to deorbit it. So it's generally considered quite a good thing to do. The risk, again, is that you need two things to get very close to each other, which comes at a risk of collision. Right. Next one, space tourism. Okay, through the orbit, Moon, Mars, maybe. Okay, controversial on this one, I think. Who thinks it's a good idea? A few. Who thinks it's a bad idea? Yeah, most people think it's a bad idea. I think you're probably right there. It's kind of considered to be risk with no real benefit. Yeah, okay, some rich people get to take some holiday snaps or whatever, but it's not really adding to humanity in any useful way, is it? I think generally what we'll probably find is that we see space, and particularly the moon, more like we view Antarctica at the moment, where it's a really unique environment that we can use to do lots of scientific testing and different industrial processes, but actually should never really be a tourist destination. Okay, got a few more. Space-based solar. What we're going to do is we're going to put a solar panel in geostationary orbit, 36,000 kilometers away. This thing's going to be the size of a football pitch. Okay? We're going to collect lots of solar rays, convert it to microwave, where it's beamed down to the UK, and give everyone in the UK access to easy, clean energy. Right? Good idea? Yeah? Something a bad idea? Anyone? There's a few bad ideas. Okay. I think most people are generally in favor of this. Technically, it's a good idea. It provides clean energy. If we did that the whole world over, then it would certainly help with our climate change mitigation. The problem is that it's not really energy security. Because I've already said, we don't know. Nobody knows what's happening in space. It'd be so easy for a meteor to hit your solar array, right? And that's your energy security gone. Worst case is there's some geopolitical risk in the world at the moment, and someone else comes and takes out your solar array, And you would know, there's no way of knowing. There's absolutely no way of knowing whether it's a meteor or someone else has attacked you. So it's a tricky one. Okay, orbital data centers. What we're doing now is we're processing our data, the cloud, in space. Okay? This is great because you have solar panels so to get the power. It's low latency to anywhere on Earth. Right? So there's a global reach to high-end computing. Is this a good idea? Yeah, a couple of you, bad idea? Most of you, yeah, okay, that's interesting. People are taking this seriously, actually. There's a lot of people looking into it. Technologically, it's challenging at the moment because we need the hardware to work in the space environment where there's lots of charged particles and it's not a very friendly place to be. There'd be another barrier, which is the communications, right, to get the data from the ground, from the user up there and back again. But those are technological challenges which could be solved in the coming years. If they are, it's probably not a bad thing to think about. Okay, space elevators. Right? Now we're going to have some really strong material that's yet to be invented that's going to travel from the Earth, from the equator, right out to geostationary orbit, which is going to give us easy access. We've already discovered that actually the launch vehicle is critical to sustaining a commercial activity. If we have a launch elevator, we don't need that anymore. We could just shuttle things up as and when we need it. Is that a good idea? Yeah, a couple of you, bad ideas? Okay, interesting, again. I don't think it's inherently a bad idea. If you can make it work, then I think it's a good idea. Again, the issue is the technology in making it work. Okay, maybe there are some issues. For example, if there's a failure, then you end up with this thing wrapping around the Earth several times. That could be a problem. It's worth thinking about. Space delivery, okay. The idea now is that what we're going to do is to deliver packages everywhere on Earth within 90 minutes, right? So you've got low latency delivery service. Who thinks that's a good idea? A few of you. Who thinks it's a bad idea? Yeah, okay, a lot of you. That's interesting. It does sound a little bit ridiculous, doesn't it? That we would have some system in place where we could deliver packages anywhere around the world within a short period of time. I think there's probably only one organization in the world that could pull this off. Santa. Okay. Okay, so the conclusion is the space sector is rapidly evolving, right? From 5 years ago to now, it has been rocketing. And that is continuing. That is a trend that is continuing now. But space isn't just for rocket scientists and astrophysicists and engineers. We need rocket scientists, physicists, and engineers. We need all of that, absolutely. But we also need the other side. We need lawyers, governance, politics, international relations, marketing. Okay? The space sector is demanding this interdisciplinary approach, and most importantly is demanding people who have ideas. And now we're at a point where ideas can become a reality because the technology is catching up. Okay, if you have a creative problem to a solution, we can now afford to try it. If it fails, fine, we'll try something different. But that's a super exciting time for the space sector, and particularly for you guys who are starting your career right now. I think you should all be seriously considering the space sector, whatever your interest, as a future direction. Okay. Thank you very much.
Okay, so thank you so much, James. Do you have any questions for James? And no questions are silly. Everything is welcome. Yeah. Do you want me to start?
For that space elevator, how high would it be, and what would it be made out of? How would you go about making something so big?
Those are all very good questions. The general consensus, the question was for the space elevator, how high would it need to be? Right? What would you make it of? And what was the last bit?
How would you make something?
How would you do it? Right. So the general idea is that it would go out to geostationary orbit, right? Because between the equator and geostationary orbit, there's no relative motion, in theory. Okay? And that's 36,000 kilometers away. The diameter of the Earth is about 12,000 kilometers, so 3 Earths further out. You'd need to make it from a very strong but very lightweight material. Carbon nanotubes are generally considered to be a good way of doing it, although any sort of distance of carbon nanotubes is yet to be demonstrated. And I think generally what you would do is you would take your port, your spaceport, up to geostationary and lower the carbon nanotubes down, and then someone can hook it on at the bottom, right? And then so there will be some lateral motion, which is, perhaps problematic. Perhaps more realistic, people are seriously looking at space elevators for the moon, right? Because on the moon, the geostationary orbit is much, much lower. So it's easier to achieve. And then we can get material from the lunar surface in a much more easy way. Good question.
Other questions? Yeah.
If satellites require fuel to stay in orbit, how can they stay in orbit for hundreds of years after the fuel's run out?
So the question was, if satellites require fuel to stay in orbit, why do they stay in orbit for hundreds of thousands of years? They require fuel to be active in orbit. Okay, so satellites that constantly have external pressure, like the upper reaches of the Earth's atmosphere, can perturb that orbit slightly and change its orbital pattern, right? Or solar winds can have an effect on the orbit as well. So all of the satellites have station keeping. They use their fuel to make sure they maintain the proper orbital motion. And without that, they will stay in orbit because there's nothing really to deorbit them. Over hundreds of thousands of years, they'll slowly decay. That takes a long time. But they're out of control in that period, so you've got no way of moving them if needed. So if there's a projected collision, for example, there's nothing you can do about it. They're just dead weight, swinging around the Earth at 8,000 meters a second.
Yeah.
You mentioned things like satellites going down in the event of like a coronal mass ejection. How can you prepare for that or plan any contingencies for that event?
The question was, how do you prepare for the coronal mass ejection events, for example? And I think the truthful answer is you can't really. Right? There are some things you can do. So if we were to put a Raspberry Pi in here in a small camera, then it would probably be very vulnerable. But military satellites are protected, right? They have much heavier encasing to try and stop some of those charged particles getting through to the dedicated electronics. But that comes at a cost. It comes at a cost of the fuel to get it up there, because it's quite heavy, and the design cost as well. So there are things you can try and make it a little bit less vulnerable, but that's really only reserved for the really important infrastructure.
Any other questions for James? Yeah.
On Earth, if someone has a oil spill,
Yeah.
tanker, someone's responsible and someone's got to pay the consequence and the price of cleanup.
Mm-hmm.
So I'm imagining scenarios now. There's a satellite in space that explodes because of an error, or there's a collision cause and it's someone's fault. Then there's a re-screen that's going to destroy like an oil spill.
Yes.
Yeah. So, are we moving toward anywhere there where there's some sort of law up there that can sort of, hey, it's your fault, you've got to pay this fine? Is that what you guys need to try and work out for the future?
Okay, so the question was, for those that can't hear, if there was an event in space and it was someone's fault, then surely they should be held responsible in some way, and what's the mechanism for doing that? And there is, right? There's the Outer Space Treaty. And that says that whoever gave the license to launch the satellite is entirely responsible for it. They hold infinite liability, right? So if a satellite that was launched by the UK comes down and it lands on someone's house, the UK government is responsible for that, and they will pay. They're liable. The problem is, if something happens in space and you have, a satellite that stops working, who's to say whose fault that is? Right? That could have been a meteor that comes in. It could be electronics that fry each other. There's no liability without proof of fault. And at the moment, we don't have the monitoring, the eyes in the sky to that space situational awareness doesn't exist to back up the liability. And actually, that's a huge problem for insurance, as you might imagine. People are insuring satellites. But until very recently, there was no way of knowing who was at fault if anything happened? And there's some really big cases with staggering amount of money where manufacturers are trying to argue that it was some meteorite or a charged particle, and someone else is saying, well, no, your mechanism failed. How do you prove that? It's in space. That's the issue we have.
Any other questions? There is no silly questions, just I repeat myself. Yeah, go ahead.
For the satellites like the GPS satellites, how regularly do they have to be replaced, or like, do they need to be replaced? Are we still using the same ones that were launched in the 70s or whenever it was? How do you go about dealing with when really important satellites fail?
Good question. So the question is essentially, how do you replenish these constellations of satellites when they fail, and when do you do that? So, for example, for the lower constellation communication satellites, they are replenished on annual timescales. So if you imagine in the future we have a constellation of 100,000 satellites, there's going to be a constant flow of things going up and things coming down again. And we don't yet understand what effect that's going to have on the Earth's atmosphere. Nobody really knows what's going to happen when we start burning hundreds of thousands of satellites in the Earth's atmosphere. For the stuff further out, it's a bit more complicated. Right? Geostationary is actually quite easy, because at the end of life of geostationary, you just move it into what's called a graveyard orbit, and that's just slightly above the normal geostationary orbit. And then there's loads of dead satellites up there. They're not going to harm anyone. The stuff in the middle is quite complicated because it's difficult to get to. And at the moment, if you looked at the defunct satellites on the screen before, most of them were that bit in the middle, the mid-Earth orbit, because it's difficult to access. It's not easy to deorbit. So until recently, we've just left them there and sent up new ones to replace them.
Yeah.
Do you think it's important that we deal with our problems on Earth before we start looking to space?
That is a really good question, and I often get asked that question. Okay, so the question is, essentially, if I can paraphrase it, why are we spending so much resources going into space and doing these activities in space when we have so many problems down on Earth? Right? And I'm not going to answer that, right? I think that's a very valuable question, and it's the right thing that everyone should be asking. What I will say is that I think that using space applications provides the foundations to our quality of life and to climate mitigation as well. So without those satellites, without putting those resources and developing the space economy, we would be ill-equipped to deal with climate change, for example, and we wouldn't have the same quality of life that we currently have. Sidestep that question.
The way we're going with the number of satellites we have in orbit, interfering with observational astronomy?
Yes, another very good question. So the question was, are these satellites interfering with observational astronomy from the ground? And the answer is yes, they are. There have already been lots of demonstrations where people have taken images of distant galaxies, for example, and we get these streaks going through it from the satellites. It is generally a problem for wide field observations, okay? Which there are lots of, but they're looking at quite a wide field, so there is still parts of that image which is still useful, even though some of it definitely isn't. And the other thing, I think that we haven't yet got to the end of that journey. I think there are ways of minimizing or mitigating that. For example, the satellite goes through the field of view in a millisecond, in a fraction of a second. It would be feasible to build a detector which detects a satellite coming to the field of view and shutters your focal plane. Okay? And that would mean you wouldn't see that satellite in your image at all. So yes, it is a problem. And actually, the satellite operators are, well, some of them are generally quite collaborative in this. And the likes of SpaceX are actually designing their satellites, modifying the design of the satellites to try and make them darker. So that's happening as well.
From the sound of things, the technology is outpacing like the lower regulation quite a bit. How fast is the technology moving, and is it going to keep technology like advanced technology? Is it going to keep getting faster?
Okay, so the question is, it sounds like technology is outpacing governance, and what's going to be the pace of this technology? Is it going to continue to continue at such a pace? And what you've done there is essentially written the title to a very good PhD project. And there are lots of people who are very interested in the relative pace of technology development and trying to keep the governance, in step. And that is exactly why we've started our new Space Research Centre in Durham, because we need the people who are working on space governance to really have a thorough, in-depth understanding, or at least access to, the knowledge of the space environment. And there are a few groups around the world who are thinking about space law, but none of them are really connected to the people who are building the satellites and understand the space environment. That's what we're doing in Durham. That's the difference that we're doing here. In terms of the pace of the technology development, that's anyone's question, right? There's new breakthroughs all the time. A lot of these ideas, though, which we spoke about in the game at the end, a lot of those ideas aren't new. They've been around since the 60s or 70s. Most of them come from science fiction books. So the ideas are there, they're just waiting for the technology to make it possible. Right? And some of that's into texture, some is in material. There's no real way of knowing what's going to happen, but what's certainly going to happen is that trend in the space sector is going to continue for at least the next 10, 20, 50 years.
More questions?
Do you think artificial intelligence is going to have a great impact on how we interact with space going forward? Or do you think it's not going to do as much compared to what we had so there?
The question is, how is artificial intelligence going to impact space activities? And yes, absolutely, artificial intelligence is impacting everything that we do. This time last year, I wouldn't have had a presentation like this with so many nice purple images. That's all done by artificial intelligence. And there's a lot of people, again, big groups, who are looking at artificial intelligence directly applied to satellites. So you could imagine, for example, a future where satellites are more like driverless cars, where they all understand their own situational awareness and they can see and communicate with all the other satellites in the area, such to avoid each other. Okay, we haven't quite achieved that with cars yet, but that's the future both on Earth and in space. The other option for AI in the space sector is really the data processing at the edge. So we're processing on the satellites now, rather than downloading all of these huge Earth observation images. What if you could process those images to get the information you needed in place in space, and then just download the answer you want? And there's a lot of people trying to take it in that direction too. Yeah.
Is there any way of enforcing rules in space, or is it just hoping that everyone agrees with it?
Another good question. Is it possible to enforce rules in space, or is it more of an agreement, right? A cooperation agreement? And I think it has to be the latter. Okay, there's no way that we can ever enforce anything in space. The problem we have at the moment is that to enforce something, you have to know what happened, as we said before. We haven't got that stage. But really, we're never going to have a single set of hard law that everybody signs up to. It's never going to happen. What we will have are agreements, right? Accords, standards of operation. And I think people will agree to that, because it's in everyone's best interest that we keep space sustainable and clean. And everyone agrees with that standard principle. So I think it'll be that more soft governance that'll take effect.
Well, if everyone agrees, why did China explode their own satellite? And do you think something like that's going to happen again in the future, or maybe in like a bigger scale? Yeah.
So the question is, if everyone agrees to these laws, then why did China destroy their own satellites to show of strength? Why was that even necessary, I guess? And I think the point is that not everyone doesn't agree yet. Okay? And everyone does agree, once they've done it, that destroying satellites is a bad thing to do. Right? So China will now say that that's a bad thing to do. Russia, they've all done it, right? Russia, China, Australia, India, they've all destroyed their own satellites as a show of strength, just because everyone else has. Whether we see that happening again, we probably will. It generally happens when a new space power comes and gets that capability, they want to show it off. Right? So they'll go and do it. They could do it in a responsible way. They could do something at low Earth orbit, which sort of comes down a bit more quickly, or they could do it irresponsibly. Generally, the international community are against it, so it's discouraged. I don't know what would happen if it came again, but there's no real way of any sanctioning happening at the moment.
Other questions? Yeah.
You mentioned how currently the main method of getting rid of defunct satellites is just deorbiting them, and obviously that's bad because they're burning up. what other alternatives are there to that? What else can you do?
I think the only other alternative is this idea of a circular economy in space, okay, where we have reprocessing factories essentially in orbit, where you get that satellite and you take it somewhere, and then you can take it apart and reprocess, reuse different components of it. If none of it's usable, then you have to think about what you do with it. Do you just stash it somewhere and then tug it out into a graveyard orbit, or even further afield? I don't know. I don't know what the answer is. I don't think anyone does. Whatever it is, it's going to be difficult because the economically viable solution, the cheapest solution, is to burn it in the Earth's atmosphere. So trying to get a company to say, I don't want you to do the cheapest thing, I need you to do this, is going to be really difficult to get them to do.
Well, so on this, in Switzerland, at EPFL in Lausanne, some students came together and started a startup. I'm guessing you've heard about them, to actually go and grab space debris and bring them back on Earth. And they actually succeeded. Was a very small thing. But so
yeah,
there are some people that...
There are a few companies out there who are actively trying to deorbit different satellites. Whether you're ever going to do it at the scale that is useful is a question.
Yeah, but you need to start somewhere.
You need to start somewhere, it's true. And the argument is developing that technology is useful in the future.
You had a question. Yeah, go ahead.
Private companies that really big research about space, also nations, and going on with that, how often the development shared to kept very private or unopen?
That's a good question. The question is about the balance of research. Is it in research institutes essentially, or in industry, and how is that collaboration happening? And it's an interesting one, and it's both. Right? There's a mix. There's a lot of R&D which is done purely in industry, okay? And obviously, why not? That's got certain drivers. And then there's a lot of research that's happening in the universities. The universities are very, very good at that ideation, the creative solution side. So the research in the university, you usually find the ideas, but they're not moving necessarily all the way to the product. In the universities, you also have the people who are building the one-of-a-kind, right? The JWST instrument, which industry aren't really interested in because they're not going to make any money off it. But at the university, you've got that knowledge base to build something which is super sophisticated. So that happens at both ends of the universities, really. And there is collaboration. The tricky bit with getting that collaboration between the university and the industry is the bit in the middle, right? The ideas come from the university, and there are some in industry as well. You then have the mid-range where you're sort of prototyping and you're getting stuff, you're testing, essentially. That's the bit that's really difficult to get funded anywhere at the moment. And then you have the stuff which is close to market. That's the stuff where people start seeing the dollar signs in their eyes, right? You can get that funded. So once you get through that hump in the middle, you're away. But that bit in the middle is still a challenge everywhere.
Questions? Yeah, go ahead.
Yeah, so as technology develops and becomes more accessible, it'll be possible for more independent organisations to send things up into orbit. So if we have all of our resources up in space, how can we actually protect, sort of police these things happening?
Yeah, so the question for everybody is, if we're relying on these resources in space, how do we protect it, essentially? That's the question. And I don't know the answer to that. Okay, we're a long way from it, and at the moment, anything in space is vulnerable, and that's a concern for lots of people, obviously. So the first step is the monitoring the facts, trying to work out where everything is and where it's going. That's step one, and we haven't done that yet.
Yeah, go ahead.
And there should be support for developing nations to get their own space programs started.
Do we think there should be support for developing nations to get their own support programs, their own space programs? Sorry, absolutely, and there is. Right. So the UN have a UN Office of Outer Space Affairs, UNOOSA, and they work very hard to try and spread that knowledge and that capability around the world, to try and get less economically developed countries into space, because it has amazing effects such as the Earth observation, to know where you need to put your pesticides and things like this, right? You don't necessarily want to buy that off the US. But it's difficult. It's difficult to achieve because the big companies are generally in the US, in China, in Russia. They don't necessarily want to make that space for people who aren't paying top dollar, right? So it's not easy, but there are people who are taking that very seriously and trying to bootstrap that, yes.
More questions? Yeah.
Do you think privatization will make like global inequality worse than because if it's just Elon Musk in his little building making all his like things for himself to get more money, it's not going to help anyone else.
Yes. So do we think that the private sector is going to be worse for global equality because the likes of SpaceX are just taking over and they're monopolizing? And that, yes, absolutely, that is a huge concern, which is why it's really important that we support other launch capabilities as well. And ESA are putting a lot of effort specifically into trying to find alternatives, because we need there to be a healthy competition for it to be good for everybody. Without that competition, then it is certainly not a good situation.
Okay. Well, thank you very much, and let's thank James again.